Hi, everybody. Okay, so this is the fourth video in the hash table series, and this particular video is about chaining as a collision resolution method. So chaining is the second closed addressing collision resolution method that we are going to look at. We're going to look at this one in maybe a little bit more details because this one is actually sort of the one that you would use if you wanted to use a closed addressing system. So with chaining, um, it is, first of all, closed addressing, which means remember that if wherever the hash function says to go, that's exactly the index where you will find the item. So the way that chaining handles this collision resolution is that instead of having effectively a second array that you would search through, what it does is it has a second linked list that you would search through. So instead of storing a 2D array, what you have at every element of your table, instead of having a record, is you would have a linked list. And what you do with your hash function is you use the hash function to really determine which of the linked lists the object belongs to. And then you would go to that particular linked list and do a search, insert, modify, remove from that list. So the hash function tells you which linked list, and then it's an operation on the linked list itself to actually complete um, the to complete the operation. So now let's take a look at how so let's pictorially look at how the idea is pretty simple. Let's look at how this would work. So this is our table. So very simply put, we have a bunch of linked lists. Now, I didn't null out these pointers, but they're effectively a bunch of empty linked lists. Okay. Now, now linked lists we've looked at a lot. We can use sentinels, not use sentinels. For our purposes, we're only drawing the linked list itself. The exact implementation of the linked list, that's a separate problem, and you can make a decision as to how you'd want to implement it. These linked lists, though, do tend to be very short because remember, you are not trying to make these long, long chains because a long linked list chain is not something you actually want to search through because it actually takes quite a bit of time to do that. So you want to keep these linked lists fairly short. And since you want to keep these linked lists short, things like using two extra nodes for sentinels may actually matter because, well, if there's only one data node and you have two sentinels, you've tripled your storage, right there. So it's not necessarily something you want to do for that reason, but it depends on how you want to do this, right? But effectively, all we're doing is we're simply going to be using the linked list as a means of saying, okay, there is everything that we're doing is just going to be stored in a node. Every record will be in its own node. We just do a linked list search. Okay, so we're going to use the same example as before. We're going to have the same set of key value pairs. So our first key is 15, and 15 goes into element 5. So let's put it there. So what it means is that we use the hash index 5 to say, oh, okay, go into this particular linked list right here. And now we simply insert into this linked list a single node whose record contains our 15 and our square. Okay? And of course, this is also the last node, whatever. Now, when we deal with minus 18, same idea. We create a single node with the record minus 18 and a triangle, and then put it into our linked list. For 10, same idea. Create a node that contains both the 10 and the star, and then we simply link it up. Now, when we deal with 25, we simply say, oh, 25, that's just going to be part of the linked list right here again. There's something in it, and it's not 25, so we're just going to add another node to our linked list. And whether you put it in the front or in the behind, that's an implementational detail that's really up to you to decide. Simply add it. Okay, whether the linked list is doubly linked or singly linked, by the way, also for you to decide. There's no rule that says it has to be doubly or singly linked. You should have probably a front and back pointer just for efficiency purposes. But effectively, it could be something like this. So the idea is very simple. And because this is a linked list, you actually never run out of room. If we end up putting that 35 example that we, negative 35 that we said before, we would simply make another node containing our negative 35 and whatever the data is, and linking it up, right? So that's all we would have to do. We would just have to have create a linked list and simply add to it or as we go. So this is chaining, okay? And when you actually implement this, the way you would do it is you would actually just declare an array of linked list objects. So for example, you take your cache list from assignment 1 and just declare an array of them. And then every operation is take the hash function. The hash function says, oh, go to linked list, index number 5. And then you would say, okay, array sub 5 dot insert, right? And or whatever operation you're going to do a search to make sure it's not there, that kind of thing, right? But all operations effectively is just a linked list operation on your on your on your on your on the linked list. Okay, so an insert, a modify, a search, whatever it is, it's all just linked list operations. And you can do it by simply calling a function from your linked list, very handy. Now, it's not without its problems. Okay, so what are some of the problems? Well, first of all, I know in the drawing it doesn't look like it's that much bigger, but remember that nodes require 2 pointers on each node. So here's one that's pretty clear that there are 2 pointers there, right? But even the ones that don't have anything, there are 2 pointers. I didn't draw them, but they're there. They take up space. And so first of all, every element, we already spend at least 2 pointers worth of data to store front and back. And then each node itself not only must store the record, we also have to add 2 pointers to the storage for the actual links, right? So it does add some increases to that. There is no, but on the other hand, it's the number of pointers that you have is really just dependent on the number of nodes that you have. So, and the increase is really only like, well, basically 2 pointers per node. So it's not like it's a terrible increase, especially if your record is actually a really big object, right? Like if your record if the size of the record is actually big, then who cares if you use 2 extra pointers at that point, right? So depending on what you're storing, the storage cost might not be that high. Now, linked lists are stored where the nodes are actually at different places in memory. And that means that when you are traversing through a linked list, you are definitely traversing through main memory. Now, why might this actually matter to you? So this is a concept that you may have encountered in other courses, and it's called the memory pyramid. So I don't know if you've heard of this before, but very quickly, we talk about memory as if it's all one thing, right? When we talk about memory, it's RAM, right? But it's actually not. Within your computer system, hardware-wise, there are actually different forms of memory, different forms of storage. At the very top of that, there's very little of this, but there is something called registers. Registers are implemented in hardware. They store very little data, and there's very few of them. So you can't store very much in a register. But if you've done any sort of assembly programming, you know that there are things called registers that you can put something into. And usually it's only something like a single integer or something like that. They're very small, but they're also blazingly fast. Okay, so this is things that you don't have very much of, but you can use. And if you store a value that you access a lot, then it's kind of worth it because right at this moment, the speed of this is significantly faster than main memory. Below the registers, you have different levels of caching. Okay, so you may actually have encountered this when you went and bought your computer, right? Like if you actually ever go and read the specs for a thing, it's like an Intel i7 with so much la 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 level 2 cache, this much level 3 cache. What the hell does that stuff mean? Well, it actually refers to storage. It's the idea that you can actually have storage that's closer to the CPU than main memory. And what happens with cache is that you actually bring data. So your data usually resides in main memory. When you access it, you bring it into main memory, into cache, so that because you're assumed to be processing this one piece of data, right? And not and it's sort of neat because not only does cache bring in the thing that you want, it also brings in things in memory that are sort of nearby. So if you're looking at an array, for example, um, this element number 2 and this element number 3 sit side by side in memory. So if I brought element 2 into my cache, element 3 is also in my cache. They bring what is called a line of memory in. Now, why does that actually matter? Well, it matters because if you start going through an array and you access a particular element, it brings in the next couple that are beside it, then the next couple of accesses is actually relatively fast because they don't have to go into main memory to get it. Whereas if you so so this is why the cache matters, right? So the thing that you might want is here, and then you can have the things that are right beside it nearby. It's already in cache. You don't have to find it in main memory. That's kind of nice. Now, um, but there's not as much of this. Then there is main and now this cache memory is closer to the CPU and it's faster. Then you have main memory, and main memory is slower. And that's when you buy your computer and they say, oh, this thing has 16 gigs of RAM, that's main memory. Now, main memory may seem pretty fast, but it's still significantly slower than cache. Okay? There's a lot less of cache memory than there is of main memory, and things in main memory are going to still be slower. Below main memory, you have generally your permanent storage. So for example, there would be things like your SSD, your hard drive. So some of you might have still like this may not this part may be no more. Okay, so some of you don't might not have a hard drive anymore. Some of you might just have an SSD at this point. But for a time when SSDs were very expensive, some people had like a very small SSD and their OS was on that, and then their hard drive was where all the data was sort of kept, and that kind of idea, right? So, but SSD is like 10 times faster than hard drive. So the idea of the memory pyramid is that as you go up the pyramid, it is faster and more expensive. Okay, so it costs more per unit of storage. So and you just don't have as much of it, and you don't have as much of those things, less amount. So because it costs more, there's less of it. Okay, okay. So that's horrible handwriting. Sorry, that's more money, smaller amount, but it's also faster. Okay, so so things like linked lists actually have a disadvantage in that sense. If you start, if you have a linked list of items, your first access, your first access to 15 doesn't help you get to 25 because you have to go into main memory for that because it's very unlikely that this node is right beside the 15 node. And then you have to do another access for 35. So because you are going through main memory for each of these guys, it tends to actually be slower because of that. Now, when we do operator counts, this is something that's never going to show up because, a plus is a plus is a plus is a plus, and access is an access is an access, right? But when it actually comes down to timing, this actually might not time nearly as well as something that you basically stick on an array, especially if you create, for example, in this one, uh, if you create your array properly, the searching through this way should be the faster thing that you want. So you actually want to probably index it reverse of how you think it should be, just so that when you're doing the search through this second dimension, you would be able to access it um, quickly from A to B, because that's the linear search that you have to do once you've determined which element, right? So that's pretty much the main thing about chaining. It's actually a fairly simple idea to understand. The implementation isn't particularly hard um, if you understand how to access your linked list. So it and you really don't want to rewrite a linked list for this. You want to work with one that you already have. It's just a matter of figuring out how to do that. And actually, I think that's it for now for this particular example. So let's stop there, and then we will continue, okay, on the next video. So that's it. Thanks.